All right, let's dive right into this. Welcome to the ultimate masterclass explainer for Cambridge Assessment International Education. I'm your master coach, and today we are stepping into a genuinely high-stakes arena. Whether you're sitting for your IGCSEs, O-levels, AS, or tackling the incredibly rigorous A-level mathematics syllabus, there is one specific topic that acts as the ultimate gatekeeper to those elite marking bands. We're talking about the theoretical architecture and the technical methodology of vectors. More specifically, mastering the equation of a line, r equals a plus lambda b. And listen, this isn't just about plugging some numbers into a formula and hoping for the best. It's about understanding precise definitions, causal relationships, and cross-topic integration. Throughout this explainer, we're going to look at real-time strategies, track performance grids, and measure your exact mark yield, taking you from the lowest foundational bands all the way up to a clean A star.
Now, I really want you to listen to this direct quote from a senior Cambridge examiner. Read it carefully on the screen. The difference between a B and an A star in mathematics often comes down to how well you understand vectors. Equation of a line, r equals a plus lambda b. Let that sink in for a second. This single equation is literally the dividing line. Why? Well, because the syllabus explicitly emphasizes the top-performing candidates don't just calculate blindly, they exhibit connected, conceptual understanding that is completely transferable to completely unfamiliar contexts. If you're aiming for those top-tier mark bands, you have to prove to the examiner that you truly understand the underlying geometry and algebraic structure. You need to show your method. Examiners award marks for the process, the clarity of your notation, and the absolute precision of your terminology.
So here is our strategic playbook for today. First, deconstructing core concepts. Second, the strategy debate. Third, the structural system upgrade. Fourth, an interactive visual workshop. And finally, the ultimate strategy recap. Let's get to work. Act 1, deconstructing core concepts and decoding those Cambridge assessment objectives. Okay, to conquer those high-tariff, multi-part past paper questions, we first have to understand the assessment objectives, or AOs. Think of the marking rubrics as scaling ladders. At the bottom rung, you have your foundational data inputs. But as you climb to the later parts of a vector question, the examiner fully expects high-level analysis and critical evaluation. You absolutely cannot just regurgitate a memorized process. At the foundation of this entire syllabus is the vector equation of a line, r equals a plus lambda b. Let's break that down. R is the general position vector of literally any point on the line. A is your anchor, the position vector of a specific known point on that line. Lambda is our scalar parameter, the multiplier, and B is the direction vector. Now, principal examiner reports continually highlight a massive critical warning. Candidates consistently confuse these key terms. The absolute highest marks are exclusively awarded to candidates who clearly define all of these terms before using them in their extended responses. The absolute crucial point here is understanding the difference between rote memorization and conceptual mastery. Rote memorization is just isolated factual data inputs. It's like having a hammer and treating every single problem like a nail. You blindly calculate the dot product just because that's the only tool you remember, without even pausing to ask if it's the right tool for finding a perpendicular distance or point of intersection. Conceptual mastery, on the other hand, is exactly what Cambridge demands. It's the ability to look at two vector lines, deconstruct the given information, select the appropriate analytical framework, and execute it flawlessly. For instance, if the question asks you to show that two lines are skew, the conceptually mastered candidate knows exactly what to do. They know they must first prove the lines are not parallel by checking the direction vectors, and then prove they do not intersect by showing that the simultaneous equations yield wildly inconsistent results. And this conceptual understanding translates directly into how you handle the specific command words you'll face on the paper. Misinterpreting these words triggers an immediate penalty on the examiner's grid. No exceptions. If the command word is explain, the examiner expectation is that you clarify your methodology. The penalty trigger? Simply giving raw mathematical data without any geometric context. If the word is analyze, you have to break down the logical steps systematically. Failing to show how you logically got from the vector equation to the simultaneous equations means you're failing to show cross-topic algebraic connections, and boom, you lose the mark. If the word is evaluate, you must justify with hard evidence. Let's say you find two possible values for a parameter. To evaluate means you test both and explicitly justify why one might be geometrically impossible in the given context. If you miss that step, you can say goodbye to the A-star band. Act 2, the strategy debate, where we navigate student response styles. Let's step into our shared study suite and listen in on two of our top scholars, Alex and Sam. They perfectly represent the two most common traps I see students fall into when drafting a response. Alex is our data-driven scholar, loves factual definitions, very meticulous. Sam is a rapid-fire writer, builds highly persuasive arguments, but almost always leaps straight to the final conclusion, completely missing the explicit restrictions set by the command words. They are staring down a brutal, complex question, asking them to evaluate whether two vector paths will ever cross. Alex looks at the paper and says, look, we just need to list out the raw facts. Let's write down the direction vectors, state the position vectors, and equate the components to find lambda. That covers the AO1 requirement. But Sam shakes their head. Are you kidding? We don't have time for a descriptive list. That'll only get us a foundation mark. The lines are skew, I can see it. Let's just write our analytical thesis right now. The lines are skew because the direction vectors aren't parallel and move on. Sam wants to skip the simultaneous equations entirely to save time. So we have a massive roadblock here. How do we bridge this gap? How do we combine Alex's purely factual definitions with Sam's flexible yet currently mathematically unsupported analytical theses? The scholars are challenging each other's reasoning live, and they are struggling to anchor their arguments to the exact requirements of the mark scheme. Alex pushes back hard, saying, Sam, if you don't show the clear notation and systematic processing, the examiner is going to dock all your method marks. You can't just guess. Sam retorts, yeah, but Alex, if you just write out a page of arithmetic and forget to write a concluding sentence that answers the actual command word, you're stuck in the core band anyway. They're both rewriting their topic sentences out loud, getting frustrated. If they submit this response in the actual exam hall, they are both getting stuck right in the middle. They need a system.
Act 3. Structural System Upgrade. But wait, strategy check? Before we unlock this top-band paragraph structure to help you crush your upcoming sessions, make sure your revision feed is perfectly optimized. Take a literal second right now to subscribe to Ace the Exams at the handle @AceTheExams and enable all notifications so you never miss our weekly Cambridge exam breakdowns. It doesn't matter if you're sitting for IGCSE, O-levels, or AS and A-levels. Hit that bell icon right now so you're always ready. Okay, let's get back to the scholars.
Our scholars have hit an unexpected structural roadblock mid-paragraph. Their evidence isn't linking back to their main thesis, so I step in as the master coach to deploy a universal structural matrix to anchor their arguments, the deconstruct, solve, evaluate framework, which is closely aligned with the Peel method, point, evidence, explanation, link. I tell them, stop arguing and follow these 5 steps. Step 1, identify given information. Step 2, break into logical steps. Step 3, solve systematically. Step 4, check for reasonableness. Step 5, make justified recommendations. Using this, Alex and Sam rewrite their text out loud, line by line. For the point, Sam confidently states they must evaluate if the lines intersect. For the evidence, Alex meticulously sets up the simultaneous equations using the components, satisfying the data requirement. During the explanation phase, instead of getting lost in the arithmetic, Alex notes that solving them yields a mathematical contradiction in the K component. Finally, for the link, Sam brings it home by pointing out that because there is a contradiction, the lines do not intersect, and since they aren't parallel, they are therefore skew. Flawless. They just engineered a top-tier response block.
Act 4. Interactive Visual Workshop. Time for some pause and practice diagnostics. All right, I am addressing you directly now. We are going to initiate Challenge 1, the Visual Data Scan. Imagine the clock is ticking down from 60 seconds on the exam room wall. You are staring at a complex vector problem. A submarine path is given by one vector line, and a torpedo path is given by another. You need to extract the highest yielding core trend from this data before time runs out. What is the very first thing your eyes should check? Are you extracting the position vectors? No, stop, that's a trap. You should be immediately scanning the direction vectors. Just look at them. Are they scalar multiples of each other? If they are, boom, the lines are parallel. If they aren't, they are either intersecting or skew. This single, 5-second visual data scan dictates whether you spend the next 5 minutes doing intense, simultaneous equations or simply write parallel vectors, therefore no intersection. Master this scan to save yourself precious exam time.
Let's move straight into Challenge 2, Spot the Examiner Trap. Take a look at this flawed medium-tier sample student paragraph on the screen. The candidate writes out a perfectly calculated vector equation. The math is pristine. But they left the terms entirely undefined without any specific context. Imagine they just wrote at the bottom of the page, lambda is 4, so the final vector is 4i plus 2j minus k. I want you to spot exactly why this just dropped a mark band. Found it? It's because they executed the calculation, but they completely failed to define what that final vector actually represents. Is it a velocity vector, a position, a point of intersection? Leaving the examiner to guess what your floating numbers mean is a fatal structural error. In fact, I've pulled the top 3 absolute worst mistakes directly from the principal examiner reports. These are the traps that consistently destroy candidate mark yields. First, confusing cause and effect within vector relationships. For example, a student assuming two lines must intersect just because they aren't parallel without actually doing the mathematical proof. Big mistake. Second, forgetting to check appropriate format and clear working presentation. Writing down a chaotic, scribbled jumble of numbers without clear labeling means the examiner literally cannot follow your logical steps, so you instantly lose the method marks. And third, providing generic answers that are not specific to the given context. If the exam scenario is about two airplanes, your final answer needs to state whether the airplanes collide, not just write the word intersect. Securing that method mark strategy relies heavily on understanding how the marks scale across three distinct evaluation levels. If your candidate action is purely descriptive, meaning you just list out the steps without any mathematical justification, your mark yield is going to be low or foundation. If your action is analytical, where you execute clear notation systematically, like Alex wanted to do, you move into the medium or core yield. But to secure that top-tier A or A-star yield, your action must be evaluative. You have to question assumptions. You must test that third simultaneous equation to justify your findings with concrete, undeniable mathematical evidence. You evaluate alternatives, you compare approaches, and you make justified mathematical recommendations.
Act 5. The Ultimate Strategy Recap and the Post-Writing Compliance Audit. Our scholars, Alex and Sam, have reviewed their final high-scoring response and realized their breakthroughs. Alex learned that factual definitions are practically useless without a systematic explanation. Sam learned that a brilliant, fast thesis is completely worthless without explicit step-by-step mathematical evidence. By merging their styles, they forged a logically flawless answer. Let's distill this entire masterclass into 3 universal Cambridge operational rules. Rule 1, the 3-step question scan for decoding. Read the scenario, identify the exact command word, and immediately highlight the direction vectors. Rule 2, the marks per minute formula for timing allocation. If it's a 6-mark question, allocate your time strictly to clear algebraic proof, not to drawing beautiful 3D sketches that yield 0 marks. Rule 3, the post-writing compliance audit. Before you ever turn the page, scan your answer. Did you explicitly state your conclusion in the context of the problem? If not, fix it right then and there. Now, to make absolutely sure this procedural framework sticks in your mind when you're under the extreme pressure of exam day, here is a quick, high-value retention strategy. Create your own mnemonic device using the first letters of key terms. For vectors, think of DSE, deconstruct, solve, evaluate. Or for checking our line relationships, think of PIS, parallel, intersecting, skew. Whatever mnemonic device you build, I want you to write it at the top of your rough paper the literal second the exam begins. This locks in the theoretical architecture and prevents your brain from panicking when you encounter an unfamiliar context. Let's do a rapid-fire summary of the core tactical takeaways from this session. First, master the theoretical architecture of R equals A plus lambda B. Second, secure those critical method marks by showing clear, systematic, line-by-line working every single time. Third, constantly verify your mathematical results against the explicit command words given in the prompt. Fourth, ensure all your algebraic evidence is directly linked back to your main geometric thesis. And finally, always define your key terminology before executing your analysis. And that brings us to the end of this highly strategic masterclass explainer. You have the tools, you have the framework, and you know exactly where the examiner traps are hidden. You are now fully armed with an elite examiner's playbook. Before you go, hit that subscribe button for Ace the Exams at 8@Ace the Exams, click the notification bell for our weekly grade masterclasses, and drop a comment below telling us exactly which Cambridge subject and level, IGCSE, O-Level, AS, or A-Level, you are preparing to conquer next. But leave here with this final thought. A B student calculates blindly, an A-star student evaluates critically. When you sit down with your next past paper, will you just be plugging in numbers, or will you be proving a mathematical truth? Keep analyzing, keep evaluating, and I will see you in the next explainer.